So it gives me great pleasure to introduce Felienne Hermans, who is soon going to be an associate professor at Leiden Institute of Advanced Computer Science in the Netherlands. She was previously an assistant professor at Delft University of Technology, also in the Netherlands, and her research focuses on end-user programming, or really how do we make programming accessible for folks who don't consider themselves to be programmers. And I particularly admire her approach because she's going into K-12 classrooms and working with teachers and students. And that's a fairly underserved community in academic research, or at least until recently. She got her PhD at Delft University as well, where she studied how software engineering principles can be applied to spreadsheets to validate them and look for errors. And a lot of that research was also spun out to a company called Infotron that's also gotten a lot of media coverage and attention. And so please join me in welcoming Felienne.
Thank you. I'm on Twitter as well, so if you're on Twitter and you want to tweet snaps of the talk, then you can mention me so I can see all the tweets later. So this talk is about how to teach programming and also a little bit about how to teach other things, because we know a lot about how to teach language and mathematics, but we haven't been teaching programming for such a long time. So it's still a field where we can learn, I think. So first, some mandatory audience participation. Who knows who said this? Everyone should learn programming. Any guesses? No? So I think every programmer ever. Isn't that right? I mean, we all love programming. We're like, programming is the best, so all the tiny humans should also program because it's so amazing. But this actually leads to an interesting question. This advocacy that many people in programming have saying everyone should learn programming leads to the question of what is programming? Because it might be the case that if I say everyone should learn programming, I mean something really different than when you say you want to teach everyone programming. And I've started to call this the water of programming, because it's very much like, maybe you know this story, this parable of three fish that are swimming, and the big fish swims into two tiny fish, and he says, "Hey folks, how's the water?" And the tiny fish say, "What's water?" To a fish, everything they know is water. So they don't really know something outside of water. They don't even understand that they could be outside of the water and it would be very pleasant. And to a certain extent, I think the programming community is a little bit like that. Many people, their friends are also programmers. And on Saturdays or Sundays, they work on open source projects. Programming is their entire life. So if you ask those fish programmers what programming is, they don't really know very well, because everything they know is programming. So I didn't wake up one sunny morning and think, hey, what is programming? This is an interesting question. This actually was due to many things that happened to me during my PhD. So I want to talk about that a little bit. I want to go back to the year 2008 when I started my PhD program and I moved from Eindhoven, which is here in the Netherlands, to Delft, which is there. So this is like a 100-kilometer move. But from someone from a tiny country, that's a big move, going outside of the state where I grew up in to another university. So like a new world started at TU Delft. And the research question that I was supposed to work on for my PhD project was researching a DSL for finance, a domain-specific language specifically for the financial domain. So we envisioned something like this, a programming language in which normal people, the non-programmers, were able to express their business problems, because we don't have enough programmers. There's not enough programmers to make all the software. So if we can empower financial users without a programming background in creating their own stuff, then that would be a great productivity enhancer. And the first thing I did in my PhD project is I went on to do an internship at an insurance company in the Netherlands. And I'm not sure if you teach that here. I'm not sure if they still teach that in the school where I went to in Eindhoven. But when I just came out of school, this was my worldview. So I thought, on the left-hand side, you have users, non-programmers. And then there's a wall in between. And then there's a programmers, a different species that doesn't really communicate a lot, doesn't really like to communicate with the users, two different people. And the users use and the programmers program. That was my worldview. This is how it works. This worldview was quickly shattered by reality, because when I was in that insurance company, I figured out that everyone was programming. They were all programming. The programmers were programming, and also the normal people were also programming. I was like, what? But they weren't programming like this. They weren't programming in traditional textual programming languages. They were programming in spreadsheets. They ran that entire insurance company on spreadsheets. Risk assessment, budgets, models, room assignments, everything was through spreadsheets made by people without a traditional background in programming. So I went back to my supervisor. I said, friends, they don't need a DSL in finance. They have a DSL in finance, and it's just amazing. And in this 4-year project, we're never going to be able to come up with something that's better than spreadsheets because, I mean, spreadsheets are code. This became the motto of my entire PhD dissertation. Spreadsheets are a programming language, and those people are programming in a spreadsheet. And I really say this without any irony. Spreadsheets are the best programming language that has ever existed in the history of programming. It's such a good programming language that people don't even know they're programming. Let that sink in. Imagine doing Java by accident. You're just like, oh, I installed Eclipse on my Windows machine, which was super easy, and then I opened it, and the interface was so intuitively, I immediately knew what to do. This said no one ever. It doesn't work like that for Java or any textual traditional programming languages, but it does work like that for spreadsheets. You open them up and you know what to do, and you can gradually build very, very complicated models without having a degree or a background or training in programming. And spreadsheets aren't just code. They have all the buzzwords, if you haven't realized this. They're functional. Because a formula in a spreadsheet, it has no side effects. The only thing a formula can do is take input from other cells and calculate a result based on that. So it's guaranteed to be side effect free. And a spreadsheet is also reactive. Because if you update part of a spreadsheet, a cell in a spreadsheet, it only updates the rest of the spreadsheet that's needed and not everything. So it's a reactive functional programming system. And yet 750 million people can use it. That's a nice goal for Haskell to reach in the future. That might not happen. So spreadsheets are code. That became the motto of my PhD dissertation. And I wrote a number of papers on how to use software engineering methods to improve spreadsheets. So for example, we worked on code smells for spreadsheets, on refactoring for spreadsheets, and clone detection in spreadsheets. And then hooray, I got my PhD. That was amazing. This all happened. And as I said, this is a story that happened, but it's a story from the brain. It's just facts that happened. They were truths. But there's a different story as well. And this is the story from the heart. The question, how was I feeling while I was doing this work? And I think it's important. We don't talk about that enough maybe in research communities. Is my research making me happy? Is this what I want? We don't talk about that a lot, and I think it's important to also talk about this. In a previous iteration of this talk, someone in the audience said, yeah, Felienne, it sounded like you were doing a therapy session with an audience. Yeah, that's a bit this. So let's talk about feelings, because I don't think we do that enough in research. So I'm really excited about spreadsheets. I loved my talk, and I also really love giving presentations and interacting with the people that might use my tools. So I went on to submit lots of talks to programming conferences for professional programmers just to interact with people. So I was like, hello friends, I'm here to give a talk. I'm a new grad student. Let me tell you the happy word, spreadsheets are code. And people be like, yeah, that's not real programming. And I was like, wait. I understand your skepticism, but they're functional programming, they're reactive, they're really cool. And people be like, not real programming. And it just went on, and it really drags you down after a while. I imagine many people in the room have a PhD or they're working on a PhD, so you know that your topic and you are like one thing, and if people comment on your topic, then it just hurts. And if they say it's not real programming, I was really feeling at the end of my thesis like, I just don't want to work on this anymore because people keep saying it's not real. So why would I do this? And it was not really a great time in my life. And it was only way later that I realized that it doesn't have to be like this. there are communities of people out there that are nice to each other. I didn't know that at the time. I really thought that, yeah, you know, if you're a grown-up and you hang out with other grown-ups, they'll just shit on your work. That's the way it's gonna be. I'm like, okay, it's not great, but I still don't like vegetables, so this is just being an adult, what it's all about. It's just not fantastic. Only until later I realized that there are people that are nice to each other. So I also very much like running, and I joined a running group somewhere in 2015. And I'm a super slow runner. My fastest half marathon is 2 hours and 10 minutes, which is super slow. I have friends that run half marathon in 1.5 hours, but they never go not real running to me. They're just like, oh, we love running. Are there people in the audience that are runners? So, a few. So runners are the worst. We're like more evangelical than Jehovah's Witnesses. If I see you running for the bus stop, I'll be like, oh, do you like running? Do you want to go in a race together? What's your personal record? And we're so like encouraging to each other. No one says like, oh, you have Adidas shoes? They have security vulnerabilities, man. You can't use them anymore. No one is like that. No one is not real running if you're slow or fat or whatever. Everyone's just like, come on, we're a community. It's like, people are nice to each other. And the same in the knitting community. So I love knitting. I did a lot of knitting when I was a teenager, but then, you know, you go to university, you don't have the time. So I sort of stopped doing it. And then in 2016, I was on a sabbatical in Cambridge, the real Cambridge. And I picked up knitting again. So I went to a knitting cafe. It was super nice. But it turned out I had old-fashioned, outdated needles. It's a bit like flesh, very outdated. So I had old needles that I got from my grandmother. But nowadays, people don't use the long needles anymore. They have circular needles, like 2 needles, and they're attached to each other with a wire. So I come in with my old-fashioned needles, and everyone is using different needles. I'm like, shit, this is going to be not real knitting. They're going to be so mean to me, but they were not mean. They were like, we love knitting as well, and we will show you how to use the new needles. People are nice to each other. Why isn't research and programming like knitting or running, or why are people mean? But I didn't realize, so let's go back to 2012. I didn't realize that this wasn't the way it needs to be. I was just like, shit. I just graduated, and I applied for a tenure-track job that they surprisingly also gave me, where I said, oh, I love spreadsheets, and I'm going to work on spreadsheets for 5 years, and this is going to be the best. But I didn't want to do it, but I had no other ideas. So I was really, really heartbroken, and I really didn't know what to do. And by a total coincidence, I ran into a bunch of kids in a local community center in Rotterdam in the Netherlands, and they needed a programming teacher. So they, through networking and people I knew, they approached me, and I thought, oh yeah, let's do some programming on Saturdays, because at least I'll do something useful for the world, even though I haven't really done any research or anything worthwhile. At least I'll be helping some kids out to learn programming. But I didn't know anything about teaching. I just started my tenure track, so I didn't really have lots of experience apart from a little bit of TAing when I was in grad school. So I didn't know how to go about teaching those kids. And then this interesting thing happened to me, because I started thinking back towards when I was 10, 11 years old, when I was learning to program. We had a computer in my home, and I just went to that computer, and it looked like this, just with a prompt. And I figured out what to do. Eventually, I don't know exactly how, I acquired a book with basic listings. And I just typed the basic listings forever and ever. And then I had something like a game. I was like, oh, I can change this variable. Oh, now everything's sideways. Oh, now everything's blue. And through that process, I learned. So in my memory, there was not a teacher present when I was learning. It was just me learning by myself, self-driven, exploring. And it's not just me. I see some people like nodding in the audience. Most people my generation that were kids in the 80s and the early 90s don't have a collective memory of how a programming lesson looks like. Which is weird, because if you think of other things, like you remember maybe how you learned to bike, probably a parent was there. Someone helped you, showed you, made sure you felt safe, and then you learned how to ride a bike. Your parents weren't like, oh, here's a bike. Have fun. But also learning language or math, you'll probably have some sort of memory of how someone explained something to you, and you're like, oh, now I get it. But most people in programming don't have such memories, and that's weird. And this leads to people giving these same type of lessons that they receive themselves. This is how I taught the kids. I was just like, you just give them some books and some programming systems, and they'll learn because they're tiny Felines, so they'll be fine. And it wasn't just people in the community lacking a memory. This idea of you can learn by yourself is also very much present in the books I bought for the kids. So it wasn't that I just said, here's some programming. I also thought, let's just buy some programming books and the kids can learn from them like I learned from the book with basic listings. And if you look at these books, of course, I didn't realize then, but looking at those books now, it's very clear that they too have this idea in mind of exploratory learning. I have some screenshots from the books. They're in Dutch because my English isn't great, but I've translated it for you because probably your Dutch isn't so great either. So here are some books. This is from Super Scratch Programming Adventure. The highlighted line says, "The best part of programming is finding mistakes." That's the best part of programming, is finding a bug and solving it, which is, it's interesting. I'm not sure if I agree that's the best part. It's a certain vision. This is also interesting. This says, programmers only learn from making mistakes. And also in Dutch, the same ambiguity is there. So it can mean, if you have a mistake, the only thing you can do is learn from it. But you can also read it as, mistakes are the only thing you can learn from and nothing else. The same ambiguity is true for the Dutch version. So programmers only learn from mistake. This is also an interesting one. There's lots here to read from this book, Computer Coding for Kids. It says, you will fail often and it will be frustrating. So imagine being a child. You pick up a book. Oh, programming, it seems interesting. And you read this. You'll fail often and it'll be frustrating. I don't know if I'm up for this. And I actually looked at some other books for kids, like learning to play the piano, because I was interested in learning to play the piano. It doesn't have things like this. It doesn't say, like, you will fail often and this will be shit, basically. It will say, let's do this together. I'm sure you can learn. Here are some things. I will be there all along the way. Even if it's a book, it has really a different vibe. It doesn't say, this is not going to be enjoyable. It says something about a community. If our books have things like, this will be frustrating. Do we hate programming? Why do we tell kids it's going to be terrible? This one, tiny snippet, but there's lots to unpack here. So the first thing says, never be afraid to mess around and experiment. And this is getting very close to this exploratory. Don't be afraid to mess around. Why wouldn't I be afraid to mess around? I don't know what the scope is of what could go wrong. When I was programming, once I erased my father's computer's hard drive. I'm sure he wouldn't have liked the books to say, just mess around. And of course, some programming language like Scratch is a little bit more boxed in, but still, a kid has no idea of the things that could go wrong. They might break the internet. They don't know what might happen. So it says something. And the next one of the same snippet is maybe even more interesting. This says, break the rules. And this is a book that's not just about Scratch, programming language without a syntax in a sense, but this book also covers Python. So in the same book, we have break the rules, but also here's some Python syntax where it really matters where the colon goes. It really matters where the square bracket goes. It matters where the space goes. If you misplace a space, Python will be like beep, 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 syntax error. So break the rules, but also here's Python. I'm so confused. And in the same snippet, there's also this. The most important thing is have fun. The most important thing about programming is fun. And this says so much about our community. So the most important thing is not learn programming so you can build an app that changes the world. Or build programming to make something that has meaning to you. No, the most important part is the process is fun. Have fun. If you're not having fun, you're doing it wrong. But also it's frustrating and you're going to fail. if you're an 8-year-old that has a good sense of life, at this point you're like, screw you guys, I'm going horseback riding. Why on earth do I still want to do programming? It radiates all these weird beliefs that all tie into this story of just let kids explore, it will be fun, it will be fine, failing is great, you'll just automatically learn from things. And as I said, at that point, I didn't have that perspective. I was just like, they're tiny me's, they'll be fine. So I thought about concepts. I said, here, this is a loop, intuitively means repetition, and this is a variable. So I definitely explained them programming concepts, because that's the stuff I struggled with when I was younger. But I didn't talk about it really, really matters where the colon goes, because I thought syntax, they'll pick up the syntax like I did. But then they didn't. They were really frustrated. They're like, oh, it's so hard. And after a while, I still observed them making similar mistakes over and over again, not really improving and not really being able to, they had an idea which seemed simple. And I'm like, okay, you can just put that in code. But they didn't. It didn't work. And it wasn't just me in my Saturday club that has observed that if you just put kids in an environment like Scratch, they will not necessarily learn. So there's this paper by Scafidi and Chambers about skill progression in Scratch. They observed the number of kids for a number of projects, and they found Scratch to have a really high dropout. So lots of kids started but then stopped, which of course could be due to a variety of reasons. Maybe they move on to a textual programming language, or just stuff happens in their lives, but it says something. And they also found sort of a flat skill level. So kids come in and then they learn a bit, and then they stay at the same level in terms of the concepts that they use and the complicatedness of their projects. And also they don't gain in efficiency. So they make the same things, and also they don't get quicker at it. So it still takes them the same amount of time to build something similarly complex. And they did this for, I think, like 2,000 students. So it shows something is going on there. We expect kids to have a certain behavior to advance, all kids, but not a lot of kids stick around, and the ones that do, the progress flattens out. So the kids were like, this is hard. And again, I cannot stress this enough. I really didn't know anything about teaching. So I don't know how stuff is in the US, but the way it works in my country is if you want to teach tiny, tiny humans in elementary school, you have to go to Teachers Academy for 4 years. If you want to teach medium-sized humans in high school, you go to Teachers Academy for 5 years. But if you want to teach university-level students, you get a PhD and 12 afternoons of Bloom's taxonomy, and then you're good to go. Which is, it's weird, right? I mean, half of our times as university professors, we spend teaching, and also supervising grad students is also about teaching. But they didn't teach me enough, I think, about teaching. So I got interested in this question, how do we teach things? And it's sort of sad that my teaching at the university, because then I was maybe 2 years into my tenure track, didn't really pose the question on me, how do we teach things? The experiences I had with the 8 and 9-year-olds in my Saturday community center were really invoking this question to me about how to teach things. I don't know what that says about universities, but in university, you assume kids are smart. At least this is what I assumed. So I thought, 18-year-olds in a good school, they'll be fine. They're struggling, but they'll be fine. And they don't necessarily tell you if they're struggling because they just got into a good school. Everything must be fine. So maybe they're struggling at home, but you don't really see. But a 9-year-old will literally take a scratch book if they're confused and hit it on the table to tell you that they don't like it anymore. The 18-year-olds don't really give you that type of direct feedback. So the Saturday Club was really inspiring me to figure out, but how do we even teach things? I think there's more to know here, and I must know this. So one of the books that I read, because I knew people that knew stuff about language education, was the Oxford Handbook of Reading, which talks about how kids acquire natural language reading skills. And it's very, very interesting. My first conclusion from this book was, we know nothing. Programming knows nothing. Not even a tiny bit, nothing. Do you know what they know about learning to read? What they know is amazing. They have all these models of hypotheses that build up on each other. So a 2-year-old sees words everywhere in the world and already starts developing hypotheses about what is and what isn't a word. So for example, if they see the word on, they say, no, it's not a word because it's too short. Because they look around in the world and they see many words and most of them are long. So this is not a word. And you can do this. They do this with children, 2, 3-year-olds. They say, is this a word? And then they're like, yes or no. You can ask them things like this. Is this a word? And they'll say, no, it's not a word because it doesn't have enough letter variety. Just all the same letters cannot be a word, which is true in most cases. And they just learn this by looking at words. So something like this, bza, even though we know it's not a word, they'll say, yeah, it's a word because it has a sufficient amount of letters and enough diversity in the letters that they think this is a word. It looks a little bit like a word. And they know for all stages and ages what hypotheses kids are having. And they also know how the hypotheses are tying into each other. So if kids get a little bit older, they start to think that something like mama is written M because their hypothesis is that letters are syllables. And this is a phase that almost all kids go through that have this type of language systems that they think, oh, I hear something, mama, there are syllables. Probably the syllables are the letters. This is their hypothesis. But then a conflict arises in the brain of a young child because this hypothesis conflicts with the idea that MM has too few letters. So even though their hypothesis that words should have more than 2 letters is a wrong hypothesis, it's still helping them to gain knowledge because it leads to a conflict. And they think, no. It cannot be a word because it has too few letters. Even though it's wrong, it's still helpful because then they reach the conclusion that letters represent sounds, that it's like mama. They know all of these things. They have entire models of what age knows what and how the things interact with each other. And if kids haven't reached the syllable hypothesis by this age, maybe there's something wrong. It's like, wow, they know so many things. I want to have a model of this for programming. Like, what are different hypotheses kids can develop about loops or variables? And even if they're wrong, they still might be helpful. And how do I even ask children what hypotheses they have? What type of questions do I ask a child to figure out how they think a variable works? So that was my first conclusion. We know nothing. My second conclusion is we lack fights in the computer science education community. And I don't mean fights because we still should be nice to each other. I mean epidemiological diversity. So why aren't there different views on teaching to program? Because in other fields, there are so many different views, and people are very explicit about their views. When I started working on programming education, I hired a developmental psychologist into my team. And one of the first things she asked me was, okay, so what school are you in? What do you believe in this research group? I was like, I understand what these words mean, but what are you asking? And I was in an engineering school. I got a master's degree from an engineering school. So it's like, we believe in the scientific truth. Are there other things we can believe in? Whereas in psychology, it's very normal that there are different people with different streams and they're very upfront about it. And if you read a paper from someone, you know, oh, they're from that school, so this is generally the things they believe. And for example, one of those debates there is in language education is phonics on the one hand side and whole language on the other hand side. I guess most people here that have kids are a little bit familiar with this, but the phonics approach is a technical approach to learning to read. So it really focuses on the letters and the sounds. So you'll do things like r, I, d, read. In the Netherlands, we actually teach kids to do this motion. I almost cannot do it without doing it because they drilled me. So it's very much about a technical skill. All the letters represent sounds, and you can just practice letters many times, and then you know how to read. On the other side of the aisle, we have the whole language approach. And the whole language approach says, no. Language is not a technical skill. Language is communication and community and connections with each other. So you shouldn't teach it as a technical skill. You should teach kids that language is a means of communication. So the most extreme followers of these type of didactics will just give kids a pencil and say, oh, you write something. And they just write random scribbles. And then the teacher says, what does it say? And the kid says, unicorn is in the forest. And they're like, great. And then by practice and by also practicing their motor skills, they will converge towards letters. But all the way they've learned that, writing is about meaning and about things that mean something to you. So this is a debate that people have in language education, which of those is best. And I'm guessing in this country, you're super familiar with the math wars. It didn't really happen like this in Europe, but it totally happened here, where in the 80s, there was this debate about how do we teach mathematics. And on the one hand side, you had explanation and practice. People said mathematics is just about knowing algorithms, practicing them a lot, and then you know the algorithms, and then you can do math. On the other hand, there were people that said, no, programming, no, math is creativity. You cannot teach people by rote practice to make a proof, because it's a creative endeavor, so you should teach kids in an exploratory way. You give them problems, and they solve the problems, and this way you foster a love for mathematics, because if you make them practice a lot, it'll be boring, and they will not like math, and they will hate it. So my question was like, wow, where's programming's pedagogical debate? Where are those two people? Why haven't we as a community, maybe we're too young, but why haven't we gone through something like, okay, these are the things you can believe, and some people believe the one thing, other people believe the other thing, some people think, it's somewhere in the middle. Why haven't we gone through this already? And it might be due to our philosophical background. So one of my friends, Alan Blackwell, says that technology is covert philosophy, which I totally believe. If you see a piece of technology, what you also see shine through it to more or less extent is what the people that made it believe about the world. Some people believe like creating something like Twitter is super great because free speech and you can share whatever you want. That says something about how those people believe the world is, that most people are nice, so our platform will be filled with nice words. Could be the case. So the same is true, I think, for education. The way we educate people also says something about the philosophy of our field, of the people that believe something. And if we say, this is how we teach, that says something about the things we believe. And this, of course, is very much related to that water of programming that I was talking about before. Similarly, we have the water of teaching programming, because we've only been taught the way we've been taught. And all our friends probably have been taught in the same way, have learned in the same way. So maybe we aren't the best people to talk about how to teach programming. Maybe we should also be outside of the programming water so we realize what the programming water is. And if you look at how people teach programming, there are certain philosophical beliefs that people have. And of course, you at MIT might be a little bit more aware of that. This is a talk I also created for other type of audiences. So you, of course, know here that Seymour Papert, the creator of Logo, was very much influenced by certain people, most famously probably by Jean Piaget, a very famous psychologist of the previous century that was the founder of constructivism. And the idea of constructivism is that, it's simple summary, it's impossible for me to put knowledge in your brain. It's just impossible. The only way for you to gain knowledge is that you construct your own version of reality. And that the things I say connect to things you already know. That's the only way that people can create knowledge in their brain. And Piaget said about Papert, nobody understands my work better than Seymour. So the creator of programming languages for kids, the pioneer of that field, was very much influenced by the idea that it's impossible to teach something. And Papert said things like, by explaining something, you take away the opportunity for a child to discover it, which very much has this belief of it's the best way to learn is if someone invents it, discovers it by themselves. So as a teacher, you should step away and just let kids learn. Which is very different, again, from how we teach other things. Because if you're caring for a tiny human and they want to learn the guitar or they want to learn to play tennis, what do? You don't buy your kid a guitar and say, here, tiny Jimi Hendrix, here's a guitar. You don't need to know anything about chords or musical notation. Just go wild. No, of course not. You get them a tutor. You get them someone that will help them practice. Practice scales and practice chords and listen to music. What does the guitar do? Hey, here's the guitar in an orchestra. Hey, here's the guitar in a jazz band. These are the different things you can do with a guitar. Show them what's there and make them practice. And this, making them practice, is very much like we also teach things in schools. So even though the guitar or tennis is something out of school, it still looks a little bit like things we do in school, like reading practice is also very much practicing a technical skill. And in math, you have the explanation and practice side of the argument that says rote memorization is the way to get people into mathematics. So beware. Controversy is coming. If you are faint of heart, you might want to leave now. If you brought your tomatoes, this is when you get them out. Because if you compare these two forms of teaching, explaining stuff to people and just having people explore, the instruction explaining phonics group is better. Research has shown this for the last 20, 30 years, that it's just better if you explain things to kids and if you make them memorize it and rote practice it. There's one paper, if you want to check this out, because you don't believe me, that's fine. There's this paper, Why Minimal Guidance Doesn't Work, by Paul Kirschner and others. That is a big study of all sorts of studies that they have done comparing these two approaches to each other. So that's something you might want to check out.
So you say it's better. How do you measure better? What does better mean?
Yeah, so that's a very interesting question. So the studies in that the paper summarizes, of course, are different. But for example, how you measure better is you have a lesson designed to explain a certain concept, and then you measure if they can do the concept. What you can also measure, and I'll have a little bit more examples later, if there's transfer from the type of thing you practice to related but different things. So a measure also of how much kids have learned from a lesson is, can they apply what they've learned to slightly different problems? That's also a measure. Some studies have also looked at the efficiency, so how much time is spent on the lesson. Is it quicker to obtain? Does it take less time of instruction? So these are all different ways. The studies in this paper are very broad. Some are about physics, some are about language, some are about math. So they also have different ways of measuring. So it depends, but across the board, this group is more efficient, better. Sometimes they've also looked at self-efficacy, by the way, at do kids feel more confident that they can do it after a lesson? That can also matter. So not only do we want to measure, we also want to understand. I think we're interesting if we want to apply this in programming, we also want to understand why is this left-hand side better than the right-hand side. So one of the studies that they've done is a group on the left-hand side gets an algebra problem, and with the algebra problem, there's a worked example. So that shows this is how you do it. These are the steps you take in an abstract form, and now here are 10 puzzles, and you just have to do this algorithm. The other group, they just gave them the algebra puzzle. They knew about the things to do, like division, and so the algebra problem was something like this, where you have to move something to the other side and divide. So they knew about all the steps, but they weren't reminded of the algorithm. This left-hand side group did way better. They took about 1/5 of the time of the other group. The time that the second group spent on just reading their problems was more than the time that the first group spent on solving all the problems. And also, this is a study where they also looked at transfer. So they didn't just have the problems that the kids got the worked example for. They also had similar but different problems. And the kids in the first group were also way better at solving related problems. So we want to understand, why is that? What is the magic that's happening here with the worked examples and the rote memorization? And for that, we have to really dig into how the human brain works. So probably you know many of these things, that human memory, short-term memory, is really bad. If I tell you something and you don't think about it a bit for a while, then you just lose the information in 30 seconds. It's gone. It's not stored in long-term memory. And we all know probably that short-term memory can only hold 5 plus or minus 2 items. This is research that's almost 100 years old, I think. It's very old, and we know that there just isn't a lot of room in your working memory to store things. And this is clear, for example, if I ask you to memorize this, it's gone, right? It's not there anymore. You didn't even have a chance to process what was there. But if I show you this, same amount of information, same amount of things, and number of different things, it's a little bit easier because you have a way, you have a strategy for storing these symbols because you can do ABK. You have a way of rolling them around in your brain, and then you're fine. At least you can remember a little bit more. And if I show you this, you can remember that. It's easy. Probably if I call you tomorrow, you'll still know this. Why? It's the same amount of information as this and as this. It's exactly the same amount. But what we do here is something called chunking. So you don't have to remember all the letters or all the symbols, because you can just remember 3 things. A cat loves a cake. So you don't have to remember all the things. You have learned how to break these symbols up into bigger parts, and now you just remember the 3 things. And this didn't happen by magic. It's because you spent lots of time on practicing these specific symbols and the words and what they mean. You looked at many cats on the internet and many cakes probably, so you know you can make a mental model of these things. And the interesting thing is, in this situation, you can also think about the problem. Maybe you were thinking, cats, how is my cat doing? If I come home, I'm going to stroke my cat because I love him. Or you're like, a cake, it's almost my birthday. And what type of cake am I going to order? You can think about those things while also remembering the sentence, because there's room in your brain for more new things. And it turns out that that room that's in your brain that's freed up by this is helping you to learn. If your brain is full, there's no learning going on. So if you look at something like this, if I try to remember this, if I really give you $100 if you still remember in an hour, you could do it, but it takes you lots of effort. Probably I feel at least my brain being full. There's no more room for something else. If I have to process this, then I cannot also do something else. I cannot think about what type of cake I want for my birthday, because all my energy is spent on this. And that energy is called cognitive load. So if a problem is so taxing for a child that there's no more room in their brain, that also means there's no more room for them to remember things. So if you look at this situation through that lens, in this second group, the cognitive load was probably too high. They look at this algebra problem, a is 4a plus 7. They're like, okay, what do I do? Okay, I could subtract 7 from both sides, and they do that. But this makes their mind full. There's no room left to evaluate what is the procedure that I'm doing. Whereas the other group gets the procedure, like, I do this procedure, and again, and again, and again. There's nothing else in their brain apart from that procedure, and this way that algorithm gets stored in their long-term memory. And then they do it on a different problem, even though it's slightly different. They have the algorithm in their long-term memory, and they can apply it. So that's probably, we don't have a reliable way of looking into brains very well yet, but this is probably the reason that these type of studies do better. So my conclusion, I think, is we need to start this fight, by which I mean a debate, of course, a nice debate where people are nice to each other, about how to teach programming. Because in programming, we've mainly heard this side of the aisle. All programming, and you've seen that through the books, maybe you remember this from teaching programming yourselves, our entire field is just filled with people that believe these type of things. And some of this is also due to the fact that this is old, and it's a long time ago. When Seymour Papert was developing Logo, we didn't know most of these things. All the studies about that inquiry learning, exploratory learning isn't as great as direct instruction, they hadn't happened before. So it's sort of makes sense that when we were pioneering programming, we didn't know that much. And other fields figured stuff out. And we're still sort of saying many things like this, radiating these beliefs to kids that having fun and exploring is super important, and you'll learn magically. So my research agenda for my new job is exploring how would the other side of the argument look like. It's still fine if people decide that they want to disagree with me. That's okay. I think programming is very much like math and language. I think it's somewhere in between math and language. So if math and language both think this is better, who are we to think that this wouldn't work for programming? So I want to explore how would it work? What are the things we could do? So one of the things I'm doing is I want to automate syntax. I want to make kids rote practice syntax 1,000,000 times and then 1,000,000 times more, so that if they're problem solving, they have no more effort. It doesn't take them any effort to write code. All their effort can be spent on problem solving and not on the syntax. So just doing things like this, simple, boring exercises, do this, put the right quotation marks there, practice that they need to match. It really matters. 1 here and 2 there is not going to work. This is one of the things we could do. A question?
Is there syntax in Scratch?
No, there's no syntax in Scratch. So this is something that we're mainly exploring for Python. But even for Scratch, you could practice pick the right block quickly. So that, because if I observe kids in Scratch, often they have a plan, they have a strategy. They're able to make a plan abstractly, and they're like, oh, I picked this block, and it doesn't work, and then they still get lost, and then the brain is full, and they forget the strategy. So I would still think that something like show them a small problem and then pick the right block is something we could do, but this is something we're exploring for Python at this point. Something else we could do, I think we don't talk about enough, is explicit strategies. And we talk about strategies quite a lot for problem solving, I think, like recursion or tail recursion. But we don't talk a lot about strategies for reading codes. And if you look at natural language, people design strategies for reading. This, again, is from a Dutch book, but this says, here's a type of reading you can do of a text. This is called examining reading. And it says the goal of reading in this way is memorizing information, which is a different goal. For example, if you read a newspaper article, maybe you're scanning. These are different forms of reading with different strategies. And they say, here's the strategy. Explicitly explain kids how to read a text. They don't know. If you have taught students, you know that they don't know how to read. You have to tell them how to read. So you say, read the text intensively. Connect to things you know. Make a scheme, make a summary, practice, explain the material to someone else. These are steps you can take. And I think we need something like this for code reading as well. There are different reasons why you're reading code. Are you doing a code review? It's different from are you deciding if you want to use this library? These are different goals. They should have different strategies. We are deliberately trying this also in a Python course, making this also for students, making them aware of different strategies. Here's a strategy, write down all the variable names. Here's a strategy, collapse all the methods and just read the method names. Some kids, you have them review each other's code, they open a Python file and they just get lost. They read it like a book. They begin at the beginning, and they read everything. And I said, have you read it? And they say, yes, I've read it, which isn't a lie. But I haven't told them really what to do. They have no strategy. And something else that we could do a lot more of, I think, is assessments. And this is mainly for the Saturday Code Club, Coder Dojo things, where everything is about having fun, and they don't do any sort of assessment, which also means teachers have a very low understanding of what kids understand. So I've been starting to do some Scratch tests in classes where I just say things like, which one is a variable? Just circle the answer. You want to make a game, and you want to initialize a variable to 0. Which one do you use? And this is not for them to get a grade, like give them a sticker or cookie, but I want to understand where they are. What project can I offer them next? What is a little bit outside of the scope of what they can do so that they will deliberately advance, because otherwise they might stick at the same level for a long time. So, of course, in every field, also in programming education, even though it's slightly better than software engineering, there are haters. There are people that say, this doesn't seem fun. When someone else presented a similar idea at a certain conference, someone tweeted, I'm not going to put the tweet here because I don't want to shame them, but someone tweeted, these people are trying to suck the fun out of computer science. So I have some good news for people that say, well, this isn't fun, it doesn't matter. There really is no research that has shown that the more kids like a certain course, the more they learn. Everyone that teaches here knows this, right? What's a good way to get great student evaluations? Make your course not very hard, and they will really like it. Have they learned a lot? No, but they really liked it. for the most part. So there is no correlation here. People think that the motivated kids are the ones that do best. This makes sense. It's like, I want to learn, and then they do well. But it isn't like this. It's actually the other way around. The kids that are doing well are motivated. It's fun to be able to do something a little bit, and a way to be able to do something a little bit is a lot of practice. So it's really like this, that the kids that do well are the kids that are motivated. So there's definitely a correlation, but it's just backwards. So it's fine if kids aren't necessarily having fun, they could still be learning. Again, talking about running, I love this comparison of programming and running. You know what's really fun is lying on the couch, watching Netflix and eating potato chips. I like that. You know what's not really fun is going to track and field training where they're making me do push-ups. It's not fun. It's not fun. No, being on the couch is fun. But I know it's making me stronger. I've seen that the effect of doing push-ups is helping me improve. Kids also know this. They might not like the act of practicing something, but they really know that if they've practiced something a lot, they have advanced, and you can remember them. Sometimes also kids in my programming club, of course, they've been in the water of programming, so they're like, I don't want to practice, I just want to play. But you can say, well, remember you couldn't read, and what did you do? I practiced a lot, and then it was very hard, the whole alphabet. This is the same. You have to practice and then you'll get better. It's really something that kids can understand, maybe somewhat better than some grown-ups. So that's it. That's everything I wanted to share. Again, my name is Felienne. I'm on Twitter as well. Before I open the room for questions, we have a moderate amount of time for questions. I want to summarize my entire talk in like 1 minute. So people that came in late, this is your second shot to get everything in 2 minutes. So it's a really good deal that you shouldn't pass over. Firstly, some people say not real programming. Please don't be those people. If you have someone coming into your CS 101 course and they're like, I did some programming in high school and it was VB6. Don't say that's not real programming. Say, we love VB6. It's great. All the programming languages are great. PHP is great and Perl is great. They're all great. They're all real programming. If people tell you they're programming, they know best. That's important. Secondly, as a field of programming, we lack a collective memory of what a programming lesson looks like. And that really is influencing the way we teach. And you see this in materials that are made for kids. They radiate beliefs about mistakes are fun, programming is about fun and not about what you can do with it. And this is probably partly due to Seymour Papert, the pioneer of the field of programming for kids, that really believe that explaining something is not the way to go, which probably was, okay then because we didn't know better, but we know better now because in all other fields, physics, other STEM fields, mathematics, science, language, we've seen that just explaining stuff to kids works best. And my personal mission is to explore how that side of the discussion would look like for programming by focusing on things like automation, rote practice, memorization, explicit strategies, and assessment. As I said, I'm on Twitter. This is my website where you can read all the papers I've written about this and about other things as well. People always ask me if I have drawn this slice by hand. I did. I used an app called GoodNotes on an iPad with an Apple Pencil, and I drew everything myself. I didn't hire anyone to do this. Pretty proud of that. And also, if you enjoyed listening to me, you might want to check out my podcast, the IEEE SE Radio Podcast. We interview pioneers from the software engineering field 3 times a month in a 1-hour interview format, and I'm one of the hosts. So if you like this, maybe you'd like that as well. We have 1 minute for questions. Yes?
In general, I'm just curious to know, what's the difference between programming for kids and then programming for adults who has never been exposed to programming in general?
Yeah, that's a very interesting question. So part of me wants to say there's no difference. I see lots of the different types of mistakes that first-year students make and that 8-year-olds make. So in a sense, there's no difference. But also, there is a difference because in terms of self-efficacy, confidence, younger kids are more confident that they can learn it. We've also done some programming lessons for people in Teachers Academy. So these are 20, 22, 23-year-olds. that are in a teacher's academy. Those are mainly women. In my country, 88% of elementary school teachers is female. So those aren't the people that have been encouraged in their entire life to care about technology